Okay, thank you. Thank you very much, even if I did manage to drive away our chair. I'm going to describe some work that was done along with some undergraduates who did some very nice work with me this year. That's Nick Rogers and Michael Nasrallah, and also Alex Walker, who is a graduate student in Karen Hinzer's group. And I would like to mention that they're part of a larger collaboration working on intermediate band solar cells that's at Ottawa and McGill and Harvard and MIT, and I wanted to put their names up there, at least briefly, before moving on. So I believe that this is the only talk on the intermediate band photovoltaic idea that's in this session. So I thought I'd give an overview of what the IBPV idea is. So it's a potential high efficiency photovoltaic architecture, which means that it's supposed to break the Shockley-Queisser limit. Now, the idea is that it could be like as efficient as multi-junction cells while being ideally cheaper to make. Multi-junction cells have the advantage of actually existing right now, unlike intermediate band solar cells. But an intermediate band solar cell is made by taking a standard PN junction in your semiconductor and then sticking a new material we call an intermediate band material in the middle. And the idea of the intermediate band material is that it has the standard band gap, but then there is a set of allowed levels that's somewhere deep inside the band gap. So the way this works is that we have photons that come in, and when they have energy greater than the band gap, they can be absorbed everywhere in the device, just like inside a normal solar cell. Over here we have an air mass zero solar spectrum, and that just shows that this portion of the spectrum, all of those photons get turned into carriers. Now, inside this intermediate band region, we can also take two low-energy subgap photons and move an electron from the valence to the intermediate, then an intermediate up to the conduction band. So we can effectively turn this portion of the spectrum with energy greater than delta E, which is this little gap here. We could take half of the photons and turn them into carriers. Now, when you do this right, you can set the voltage by this large band gap of the outside. So you can keep a large voltage while increasing your current, which ideally under fully concentrated sunlight can give you a detailed balance efficiency limit of 63%, or in one sun, 47%, so about 50% increase over the Shockley-Queisser limit, which is why people are interested. Now, the problem for these is that deep level states inside the band gap are well known to be non-radiative recombination centers, which is a big problem for all intermediate band devices that have been made so far. And so I'm not actually going to, I spent a lot of time working on this problem, but I'm not actually going to talk about a lot of it today. What I will be describing is some work in progress to sort of define what we are as goals for the community of making intermediate band solar cells, which is, it's remarkably not entirely clear yet. So this is a figure that did not transfer correctly. I didn't intend to just give you little text snippets from papers. I apologize for that. Warning, if you crop your figures in PowerPoint, sometimes this happens. I don't know why. The physical materials, there's supposed to be a nice picture over here from Zetian Mies of a nanowire with quantum dots inside it, which is being explored for intermediate band solar cells. And at Harvard and MIT, they work on making on something called hyperdoped silicon, where they put very high concentrations of sulfur or selenium inside silicon. And there's a nice figure here showing how well that absorbs subgap light, but you'll just have to trust me on this. I'm a theorist, and there won't be that much more experimental pieces. So I promise I have looked. Not all of my figures look this way. So this is what I will say, though, is that the best intermediate band solar cells that exist so far, which are in papers, which have this text in them, are inside a zinc telluride doped with oxygen system, or a gallium arsenide, gallium nitride arsenide system, both of which have been shown to have intermediate bands and to have the intermediate band effect inside them, and both of them have efficiencies well below 1%. And so the challenge that we have as an intermediate band research community is how to go from these less than 1% efficient cells and devices that we have now to this goal of being highly efficient, 63% being the absolute limit of how we can go there. Now, those of you with extremely good memories will know that last year I spoke at this conference about a potential idea called lifetime recovery, which is a shortcut to go from these terrible cells we have now to the highly efficient ones that we want to have. And in fact, what I talked about last year is that does not work. This is some work about non-radiative recombination, which I'm not going to say further about, but it has been published since I was here a year ago. What I'm describing today is some work trying to describe how good we need these cells to actually be, to try to let us know where we are, so that you don't actually have to make devices. We are not at a point where we should be making solar cells. We should be studying absorber materials and not worrying about contacts and a whole bunch of other things, and to know what do we actually need as material parameters for this system. So this is not a revolutionary concept, but I proposed this figure of merit called which I call nu, which is just for this device where you have p-type, n-type, and the intermediate band in the middle. Take the non-radiative trapping time for a carrier, either electron or hole, to be captured into the intermediate band, divided by the transit time that it takes a carrier to move through this device. Now, depending on what you use for your intermediate band photovoltaic system, you may have a drift type device. So for example, if you make your intermediate band out of quantum dots, then there's likely going to be an electric field that sweeps the carriers outside this region. So if the intermediate band has a width of w, then the transit time is just given by the width divided by the velocity. Thank you, first year physics. And the velocity is just mu times the electric field, which we can estimate as the built-in voltage divided by the width itself. And so the key here is the transit time goes like the width squared. Now, if it's a diffusive, for example, the doped intermediate band models, then we always have our transit time going like the distance squared divided by some diffusion constant. And we can relate the diffusion constant to the mobility using an Einstein relationship. So in both cases, we end up with this relationship where the transit time goes like the width of that little layer squared. Now, that width is something that if we have a good intermediate band solar cell, we want to absorb subgap light. So we want to choose that width. It's a bad region. We want to make it as small as possible, but we actually want to absorb light. So we want to choose that width to be on the order of 1 over the subgap absorptivity for the material. So exactly where that, light trapping effects, exactly how much it needs to be, this is the order of magnitude of it. And what this means is that we end up with a figure of merit that ends up the same way, whether we have a drift or diffusive material, where we have the tau trap, the mobility, the subgap absorptivity squared, and then either a built-in voltage or temperature. Now, if you are just in the diffusive limit, this is the same thing as the diffusion length times the absorptivity squared. Okay, but in the drift case, there's no real equivalent. So the point is that all of these are measurable parameters for your absorber material alone, and the thing we want to know, okay, it's great, so we want this figure of merit to be large. How large do we want it to be? So what we want is to have a model for a device so that we can answer this question and give goals for material design. Now, if you have a drift type device, then your band structure will look something like this for your intermediate band P system. And there's a nice model that's already in the literature that describes how these should work. But there isn't one that describes what happens when you have a really high density of states inside your intermediate band. And so instead of having an intrinsic-like region over here, you have 2 junctions inside. So that's what I'm trying to fill here in this work. So the idea is we want to make some analytic approximations so we can get an analytic 1D model for how this system works. And what we do is we look inside at this junction and make a depletion approximation. So over here we have a conduction band carrier concentration that's just equal to our dopant concentration. Inside of some region inside, we completely deplete our conduction band carriers, and we fill, the F is the filling factor for the intermediate band levels. We fill them up all the way to 1, which makes it look like the p-type side of a standard NP junction. And then we reach our whatever other equilibrium levels are deep inside. And so there's a question of what exactly this width should be. And then at this junction, we again have something that looks a lot like a classical NP junction, except now the intermediate band is playing the other role. Now it's playing the N-type role, and inside the depletion region, it is completely depleted. And so that's our charge transfer giving us our built-in voltages. And so what we want to know from this model in order to make predictions for the solar cell is what are the built-in fields for this, what are the depletion widths, and what are the boundary conditions. Then we can actually solve for J of V in generation. So there's a lot of not particularly complicated, but too long for this talk, derivations for getting all of these different pieces. I will just try to emphasize what are the approximations that go into it. So I mentioned that there's depletion. We're putting the intermediate band at a single energy level with a filling factor, and assuming that the junctions are very thin. So for in this limit and the extreme limit, the junctions are thin, so we neglect the recombination processes inside the junction. It's just sort of a crude first approximation. And this gives some analytic formulae. I don't actually mean these to be very interesting. It's just to say that they exist for the built-in fields at the PI junction, the depletion width, and one of the boundary conditions at the edge. But one of the things we'd like to know, so I can tell you, and on the next slide I'll show you some results that come for the efficiencies based on this model, but one of the things we'd like to know is whether this model is accurate. And so that's where Alex Walker in Karen Hinzer's group comes in. So he has been testing this using some modeling in Synopsys Centaurus, which is very good at being able to model these away from these assumptions. It does not have the ability to model an intermediate band material when it is illuminated, but in the dark we can test a lot of the assumptions from my analytic model, which can deal with sunlight. So we take a system that's based off of gallium arsenide with some doping profile. It has an intermediate band level that's about 0.27 eV away from the edge, which for a gallium arsenide band gap is the right place to put it, and you end up with a whole bunch of things for the band structure and for the electron and hole densities and the electrostatic potential. And so we can look at the different features that have come out from the Centaurus model, and we can compare them to these predictions over on this side. And I'll just put up here and say that predicting the built-in fields we can do to better fractions of a percent, and probably can make that even better. Getting these the boundary condition at the edge of the depletion width on the left side, which is less important for details, we're within 10%. On this side, it's a factor of 5, but we do have a carrier concentration that's moving by 16 orders of magnitude. So I'm pretty happy with something that's only off by about a factor of 5. The depletion widths were off by about 100%, factor of 2 inside them, and we're trying to understand why that is exactly. But the point of this is this is preliminary so far, and we're trying to take this to find out where the model works, and most importantly where it doesn't, so that when I put results up like this, we know which of this plot is the region you should believe. So this is the conclusion mostly of what is the figure of merit, what is the efficiency of a solar cell in this model versus the figure of merit. And so I've taken here a solar cell that has a band gap of 2.4 eV and an intermediate level that's 0.9 eV below it, which is the optimal unconcentrated intermediate band solar cell choices, black body, unconcentrated sunlight, and made the P and N perfect, because I don't want to study the problems that come from the P and the N semiconductors. I want all the problems to be in the intermediate band region. And then modify this figure of merit. And so what's going on here is a little noisy because the simulations aren't fully converged. That's a problem with work in progress. But the point is that in this region, what the simulation says is make that intermediate band thin. We don't even want it. We don't want the absorption that comes from it. We just want you to get rid of it. Please remove it. The cell is better if it weren't there. Okay? That's what we wanted to know. That's the region that people are currently making intermediate band devices in, which is why their efficiencies are so poor. Now, what's happening above that is where your intermediate band is actually improving the efficiency of the device. That's where you want to be. And the important part for me is that in this model, in these parameters, the breakpoint for those is just about nu equals 0.5. And that's the goal, because I have experimental collaborators who are measuring the figure of merit inside their materials. They're not at 0.5 yet, which says don't bother to start making devices. Try to figure out how you can increase the absorptivity or the lifetimes inside them, or the mobilities, so that you can get to this 0.5. And once you're above that, then is the time that you should actually be looking to expect to find an improvement coming from your intermediate band cell. So this is just the beginning for this particular choice of band gaps, which doesn't correspond to any particular material, but it's beginning to point the way forward. So I'll just put a brief summary here that, it's sort of obvious we need strong subgap absorption. We want to not have non-radiative recombination processes, but to quantify that, we want a figure of merit that's about 0.5 or greater. And I should mention, for those of you who are looking for new homes academically, I am in the market for master's or PhD students, so please feel free to come talk to me or tell your friends. Thanks very much.